Greetings, the Astro 30 here yet again, and welcome back to AEL. Now, if you're new to this channel, please consider going down below and subscribing if you haven't done so already. That'll help me out immensely. Now, this is the pure definition of electronics porn. I swear I buy it just for the articles. Okay, yeah, that's a terrible joke. This is this month's edition, and I haven't bought this magazine for a good 6 to 7 years now, and I thought a couple of weekends ago that when I was out and about, I'd go and, purchase one, and I'll see if I can find one, just to see how much this thing has changed. And it's changed a little. So I do tend to remember that these used to be a little bit bigger. Maybe, maybe not. So from my standpoint, most stuff is the same. They're now flogging more like online shop and silicon chip kits. They still have the circuit notebook, which may appeal to some people. The serviceman's log has changed. It used to be by one guy, repairing various different things. Now it seems to be by multiple people. There's vintage radio here, which deals with a lot of Astor radios and stuff like that. It's like having Mr. Carlson's lab restoring a radio in an Australian electronics magazine. They still have the Ask Silicon chip, advertising and market center crap. But they now have a section here called Mini Projects, which never used to be there. And what piqued my interest, because nothing else in this magazine does, well, not this issue anyway, is a Discrete 555 timer. And I thought to myself, because for about a year now, ever since I started presenting videos on the 555 timer circuits, I thought to myself I should probably implement a discrete version using transistors of a 555 timer just to see if it can be done, because I don't think anyone's done it. What is the point of doing that though, considering you can just buy an IC? Well, it's not for a practical purpose, it's more for, learning purposes, like to see how the circuit actually functions and stuff like that. So if I turn to page 20, this is a bit confusing, but if I turn to page 20, there it is there, the Discrete 555 timer, and this is by Tim Blythman, and for some reason it says J-Car and silicon chip, so this is probably sort of the same idea as the short circuits range, which was released by J-Car, and because J-Car and silicon chip seem to be in bed with each other, well, yeah. So here's a look at what a 555 timer basically is, and this is somewhat from the data sheet. We have the threshold, the control, and the trigger pins, and the discharge pins. The reset pin is not shown, but in 99% of cases of using a 555 timer, that pin is tied to the VCC or high. And I found through the use of a 555 timer, a traditional one, that pin doesn't need to be connected to anything. It only matters when it's brought low, does the output become low and the oscillation stops. The 7555 timer, however, does need the reset pin tied high or it will not oscillate, the output will be low. So that's the only difference between the two ICs. But we've got two comparators and this potential divider here made up of these three resistors. In the 555 it's 5k resistors each. You can't get 5k resistors, not in metal film anyway, and it's 4.8 or 5.1. So, but for all practical purposes it doesn't matter what the value of this resistor is. It could be 10k, it could be 22k. All it's doing is setting the supply voltage to 2/3 for the first comparator, the threshold comparator, and 1/3 the supply rail for the trigger comparator. and then it goes into a latch, or a flip-flop. So when this is set or reset, this latch will remain in either of those states, either high or low. And we'll notice that on the output pin here, it's marked with a underscore above that. That means not out. So that means the output is the reverse of what the input is. So say the input was high, the output would be low. And conversely, if the input was low, the output would be high. That's then put into an inverter, which then drives the output. So when this is low, the output will be high. And the thing is, if this output becomes high, then this discharge transistor will turn on. And this is very important as to why this is a not out. So in a normal operation, we want it to start oscillating with the output at a high state. So this is low, which brings the discharge to low. And with a resistor and capacitor in the off-stable configuration across these points, well, it will start at high, it will discharge the capacitor. Once the capacitor starts to recharge, then this comparator will take over, which then brings the output low, and brings this high, which then turns the transistor on. So then that discharges the capacitor, allowing this to become high again, recharging the capacitor and starting the cycle over again, and so on and so forth. It's pretty basic as to how that works. And there's their practical diagram of a typical off-stable oscillator that I was talking about before. So this is set so that pins 2 and 6 are connected together as they traditionally are. Pin 4 is tied high to the VCC. We've got one resistor here, one resistor there, which is charging this capacitor here at the threshold pin. So once this capacitor is charged to 1/3 the supply rail rather, then the output will switch to low, which then turns the discharge pin on here, which will then discharge the capacitor back to ground, bringing the output back to high, and so on and so forth. And that's basically how the 555 timer operates in off-stable mode. And there's their circuit diagram for the 555 timer that they've implemented. Now it uses, from what I can see, 5, 6, 7, 8, 9 transistors, and they're common transistors, all BC547s and a couple of BC557s. So we've got two comparators here, and this is the latch over here, which is basically a flip-flop. This LED is said to be put in circuit to help the loading on this latch, so it's not, it keeps it more stable, basically. So it may be important to include this. There's the discharge transistor, and there's our output point. And that's basically it. It can be built up in probably half an hour on a piece of breadboard, and that's what this is designed to have done with it, is be built up on breadboard. So I'm going to build it up on breadboard, and we're going to test it out to see if it actually does work. They've designed this to run at 5 volts, but I'm pretty sure that this can run at a higher voltage considering the transistors we're using here. I don't see any reason why it has to be 5 volts. It may be at 5 volts because it's designed to run with circuits that operate at 5 volts. But whatever. So let me get to building this and we'll test it out. Basically, this is over here is a suggestion of how you can test the circuit. So we'll put it into an off-stable flip-flop, etc., and see how it works, because in its current layout here it's not going to do anything, so we need these external components to make it work. So I don't have a 2K resistor, I'll use a 2K2. There's no parts on here that they're using that I don't have, so yeah, excellent. It is using quite a few 10k resistors though. And with their potential divider, they're using 10k. So there's one here, one there, and the third one is there. So that's the 555 basically. So let me build it up, give me something to do for an hour, and then we'll come back when it's built. And a short time later I have actually got the circuit built. It's a bit convoluted and all over the place, but I tried to lay it out as best as I can. This wire just floating around in the breeze here is our control voltage pin 5 basically, for all intents and purposes. In figure 2 of the article it says that they're putting that pin to ground. I'm leaving it floating for now. So this is the first preliminary test. This LED is the LED that's in the main circuit to keep the latch a little bit more stable. This other LED here is connected to the output and tied high. So when the output is high, this LED should light up. And these components over here are the stable oscillator external components. So I've got a 1K, a 2K2. The junction here one goes to the threshold input, one goes to the trigger input, and that capacitor is then tied to ground. No, it's not. It's tied to positives. That's completely wrong. So that should be going to ground. Alright, turn it on, see what happens. Absolutely nothing. Alright, so let me ground the other input and it's not doing anything. I'm at 5 volts on my supply and the circuit is failing to function. Well, isn't that disappointing? Because, well, it should. And this is the first silicon chip article or circuit that I've built that doesn't work. Now either it's me, I've wired something incorrectly, or I've got a dud component. So I already tested this off camera before I started shooting and it didn't work, so I wanted to show that, yeah, it doesn't work first off. So I didn't notice that this was an error, but I've corrected that now, but it still made no difference to the operation of the circuit. Something is not right here. I don't know what. So I'm going to have to go through. I'm going to leave that grounded, I guess. I'm going to go through and just check my wiring for a third time and see if I've miswired something. I don't know. But it is kind of disappointing that I haven't got a working circuit to show you. But it is what it is. So let me do some investigation and I'll come back. Well, we've got progress. I now have an LED illuminated. That transistor was not conducting base collector or base emitter. So this transistor is dead. But it's still not oscillating. And I can't figure out why it's not wanting to oscillate. So far I found one dead component, but all the others check out fine, so I don't know what's going on there. That's the discharge. Yeah, that's very disappointing. So I've stared at this bloody thing for the last hour and I cannot find a wiring issue or you know, anything physically wrong with the circuit. So either the schematic is wrong, which is highly possible, or I'm done something that I'm just missing. I just cannot figure out what the problem is. Maybe the comparator circuits aren't functioning correctly, or the latch is not functioning correctly. Probably due to a poor layout, or something like that. I don't exactly know, because both bases of these two comparators on the threshold and the trigger pins respectively are at the supply voltage, because they come off the same point here. So they're going to be around about 5 volts. So both comparators are seeing 5 volts at their input, which technically speaking is what's supposed to be there, but it's not switching it from a low state, which is what this LED over here is indicating, to a high state, and then allowing the discharge transistor over here to turn on, to then discharge this capacitor, to then switch it back over into a low state, charge, go to a high state, and flip-flop that way, but it's not doing it. I even put the control pin, which is the floating base of the first comparator, to ground via a 100 nanofarad capacitor, but that didn't prove anything either. Because if we bring the base directly to ground, as they're shown in figure 2, which doesn't make sense, you don't normally bring the control voltage pin to ground unless you want the circuit not to oscillate at all. Yeah, I don't know. I can't figure it out. There's no damaged components, everything is fine. I've gone through and checked my component wiring 10 times now, and I just cannot see the issue. I don't know what happens when we remove the emitter of that. Absolutely nothing. Okay, if I take the transistor out of circuit, nothing happens. So yeah, it's leading me to believe that there's something wrong with the latching circuit over here. It's just not doing what it's supposed to do, which is highly annoying. Okay, so I got my multimeter in voltage mode hooked up to the circuit on the negative, and well, at the positive input we've got the 5 volts there. At the junction point of the capacitor and ground respectively, we've got the supply voltage, which is okay, fine. At the base of the first comparator, we also have that 5 volts. At the base of the second comparator, without shorting things, we also have that 5 volts, because, well, it's wired to the same point. At the collector of this NPN transistor, which is on the second comparator, we've got diddly squat, bugger all. So this transistor is conducting, and on the anode of the other diode on the other side, we've got 1.5 odd volts there, and of course on the other side of it we've got about a volt, which is turning this transistor on, which is bringing it's supposed to be bringing emitter up to something, but I've just noticed the emitter is open. That should be going to ground, I believe. Yes, I have not. You're kidding me. After an hour I finally see an error. Wow. This transistor here, its emitter, is open. It doesn't go anywhere, so I'll just connect a wire to ground somewhere. Well, what do you know? It's working. You have got to be joking me. All this time it was an open emitter. You bastard. Alright, okay, so we can see that it's working. This transistor over here, which drives this main LED, which is in the circuit to start with, it shows the state of the output. So when it's lit, the output is low. When it's not lit, the output is high. And according to the description, it's also supposed to even the load on these two comparator memory transistors, just to keep them even and symmetrical. And as we can see, we're oscillating, if we ignore that LED, We're oscillating at about, I don't know, 2 cycles per second, something like that. It's 1K, 2K2 and 100 microfarads, so you could use the datasheet's calculation to work out what the frequency is, but it's going to be roughly about 2 Hertz. That is just off tap. I mean, I looked at the circuit 10 times and couldn't see that emitter was open. It's amazing. I was mainly concerned about, you know, things being shorted together and all the resistors and diodes and stuff being actually routed correctly throughout the circuit. I didn't even notice this bloody pin over here. What a stupid rookie mistake that was. So it's good to see the circuit's working. It just proves that basic building blocks like 2 differential amplifiers for comparators, that's what they are, and a flip-flop circuit over here, which is, well, basically monostable, so when you give it one particular potential at one input, it forces the other one off. The converse is true. You give a potential at the other input, it forces the first one off, and the cycle repeats depending on which one is being triggered. But it will stay in that state until another trigger is given to it. So take, for instance, this transistor here is the reset transistor, and this transistor is the set transistor. So as soon as a set voltage is applied, the reset transistor stops conducting, and the set transistor keeps the reset transistor from turning back on. Conversely, if you give the reset transistor a input trigger, it'll turn the set transistor off, and it will keep the set transistor off until another set trigger is presented to the circuit. So yeah, it's basically a one-shot flip-flop. So one shot on that side, it flips into one state, one shot on the other side flips into the other state, and remains in that state until acted upon by another trigger. So I'm going to probably say that I'm going to leave this video here because it's gone on probably long enough as it is, and it's going to be fun to edit because I've got to cut a few things out of mis-talking and all that sort of rubbish. But I'm not going to go into too much. That's fine. I'm not going to go into too much about testing it on different configurations. I mean, it probably will work. What I do want to know is, now I've lost that connection altogether, what I do want to know is if I take that capacitor back out that I put in there, the 100 nanofarad, and bring this base to ground, it stays in a high state. So what is the point to doing that? There is no point. So you don't ground the control input, because that makes absolutely no sense. Although me touching the wire is causing it to change state, which is interesting. But yeah, there should be a capacitor to ground off of that input because it's not being used. So I'm going to put that back in because it seems to work fine. Probably not doing anything. And if I brought that to positive, what would happen? Not a great deal. We're also not really interested in PWM control with it either. But it's up to experimentation. I may revisit this later and play with it and, you know, see what varying the voltage here at the control pin does to the operation of the circuit. But for now, I'm going to leave this video here. And if you enjoyed it, please remember to go down below, like, comment, subscribe if you haven't done so already. And as always, this is Yastro30 saying, see ya, have a great day, I'll see you in the next video. Thanks for watching.